Hi guys, today we will be discussing a LeetCode problem of the day, that is LeetCode 144, which is binary tree preorder traversal. So it's an easy problem, and for solving this problem you need to know what is a binary tree and what is a preorder traversal. So let's quickly start discussing the problem statement and the required concept for this problem. So it's said that we are given the root of a binary tree, return the preorder traversal of the node's value. So first question is that what is a binary tree? Binary tree is nothing but a data structure in which each node has at most two children. So this is a binary tree. If I say, because there is a root node and it's had at most two children, and if it's going to be having one more children, then this data structure will not be called as binary tree, as the name says that it is like a binary tree, so each node can have at most two children. Or this is also a valid binary tree. So this has two children, this has zero children, this has two children, this is all zero. So each node can have at most two children, so this is a binary tree. So this was the concept you need to know about for the binary tree. Then we are said that we need to return the preorder traversal of this tree. So there are three kind of traversal possible in a binary tree. These are preorder, in order, and then there is a post order. So what in pre-order what we do is, in pre-order what we do, we first in pre-order we first print the root value is printed first, then we move to the left subtree, then we move to the right subtree. What we do in order, we move to the left subtree, first the element of the left subtrees are printed, then we print the root element, then we move to the right subtree. In the post order what we do is, first the left subtree is printed, then the right subtree is printed, then we print the root element. So you can see based on the position of the root, if the root is printed first, we call this as pre-order. If the root is printed in the middle, then we call it as a in order. If the root is printed at last, we call it as the post order. So this was the three kind of traversal that is possible in binary tree, or these are major three kind of traversal in the whole DSA. So this you can refer. So as you might have already guessed that there we have to do some repetitive tasks. So this solution is we have to use recursion to solve this question. So let's quickly move to the solution of this problem. So let's start understanding how the recursion work in this problem. I will be taking a sample tree like this one. It's gonna have node 2, 3. So as you can see, this is a valid binary tree. So this thing, the left subtree is this part, this whole tree, so we will call that L, and the right subtree is this part. So we will construct a function that is solve. Let's name the function as solve. What it will do, what we will do, we will maintain an array. What we will do, we will just print the root node. So first we will do the printing of the root node, print root. Then what we will do, we will call this solve function, and it will give us the printed value of the root. The call first step is, let me write this the statement what I told. Call solve for left subtree. So we call the solve for the left subtree. What it will do, it will guarantee that we get a printed value of the left subtree. So we got the root, we got the printed left subtree. After that, what we'll do, we will call solve for the right subtree. What it will guarantee, that it will give me the printed right subtree. Got it? So like while doing the recursion problem, you need to like think of a function like recursively. You don't need to implement the function, but you just need to think like what the function is going to return. So it's like there is concept called as leap of faith, I guess. So I am just trusting this solve function. I don't know how it will return the value, but I know it will return me something, and using that I will solve my problem. So let's dive more deeper in this recursive problem. So we got like when the like we call the left sub to solve, when we call this solve function to solve this left subtree, it will do the same procedure. It will take 2 as the root, it will go for the left subtree, then it will go to the right subtree, then it will like return the value for this 2 root, and the 2 root will return for 1, then 1 will go to the right subtree. It will then it will make 3 as the root, then 3 will call for the left subtree, then go for the right subtree, it will return to 3, then 3 will return this result to 1. So this is how the recursion is working in this problem. So now let's see the code. What I did is actually I created an answer vector, because the function the LeetCode has provided us is like wanted a vector in return, so they will like take care of the printing part. Then I call the solve for root and answer. As I told you, like first we will pass the root node here. So when I pass the root node here, this is the like solve function. So it take 2 parameter, root node and a reference to the answer vector. So I'm not passing the answer vector as a value parameter, I'm passing it to the reference, so it will save like memory. So this is like stored single like once in the memory. We don't need to create copy of this vector many times. So this function is kind of a void type. So it will do what it will do. First, like there is a base check. If our node that we are passing is null, then we are going to simply return. Else what we'll do, we will like print the node, like print the node. Yeah, just answer.pushback is similar to printing the node. So this is like printing the node, printing the root node, sorry, printing. Then we call the solve for the left subtree, right? Node, we are passing the root node, root as the node left. So it's like solve left subtree, and after that what we are doing, we are calling for the right subtree, solve right subtree, then we are returning. Okay, so this function is this is how the recursion is working in this like problem. So as you can see, the solution was very easy. We simply like need to understand the recursive concept and the concept of this pre-order, in-order and post-order traversal and the binary tree concept. So if like this is the recursive solution, you can refer. Now let's quickly discuss the time complexity and the space complexity of the solution. So if I discuss the time complexity of the solution, it's going to be OFN. Why? Because we are visiting each node once. And for like the space complexity, like it's gonna be OFN. For the space complexity, it's going to be OFN, because what we're doing is like we are making recursive call, right? And we know that recursive call uses stack, right? So like the recursive call uses stack to maintain the order of the function that it need to call in order. So at max what can happen, the stack can take at max like if I say there are n nodes in the tree, the stack can take at max n memory locations. So that's why the space complexity is gonna be O of n. So let me write this clearly for you guys. So this is the time complexity because it is O of n, because we are visiting the visiting a node once. So whereas the space complexity is also going to be O of n because we are visiting the we are making recursive call, and recursive call uses stack. So that's why this space complexity is going to be O of n. So guys, so this was the recursive solution for this problem. While there is an optimized solution for this problem, like that is known by the name of Morris traversal. I also learned the solution today while solving this problem. So it's like very helpful if you mention this solution in your interview. It can get your chances increase your chances to get selected in the interview, because like many less people know this traversal. So basically what we are doing in this traversal, what the main issue that this Morris traversal is trying to solve is, like in recursion, we are using a stack to store like function calls, I guess. So this takes memory of O of n. So let's think of a scenario where if we reach the end of the tree, like if I reach here, let me draw the tree again. If we consider a scenario, if we reach the end of the tree, we just we somehow jump to the root node again, and from that we can continue our traversal. So this is like the basic idea of this Morris traversal. So what it's trying to do is, like whenever you hit the end of the tree, it just traverse to the root node, and from that you can start your computation. So let me draw a subtree like this. I will take only this thing. So like this. Okay, so this is our root, right? First condition, what how this Morris traversal work is, check for root left. If like this root left exists, if root left is null, let's say if it equals to null pointer, then just print the root node. So I will say print root, else find rightmost null rightmost last node. So what I just said is, like if the root is if the root left pointer is null pointer, just print the root, and if it is not null, you need to find the rightmost last node in this particular subtree. So here you can see we have a left node, we don't have a right node, so that's how this second node is the rightmost node. And if we look for this subtree, right, this third, if we take the node as 3, then the rightmost node will be 6. So like for this 2, we don't have any right node, so like automatically 2 will become the last rightmost node. After like getting the rightmost node, what we'll do, we will set the right pointer of rightmost sorry, not null, we will set it to root. So you can see that I'm creating a link here. So when this 2 will point to 1. Okay, then after setting the rightmost pointer to null, we will just print the root and print root. Okay, so this is like the first phase of the like Morris traversal. After doing this thing, what we will do, we will move root to root left and repeat our steps. So similarly, like 2 will then after root 2 will become the root, we have to just check for this thing. We will go to the left of the, we will find the rightmost node in the left side. So here I can see 4 is the rightmost node in the left side. We will point it to 2 and then we will print the, like we will add to, like we will print the root, then we will move to this 4. 4 will become the root node. It doesn't have any right node or the left node. So for that 4, when the 4 will become the root, it doesn't have any left node, like the left node is null, left node pointer is null. So what we'll do, we will just simply print the 4, like print 4. So like if you have like consider the order, first we print 1, then we print 2, then we printed 4, and after like printing 4, what we will do, we will just move to the current right. So it will move to the second part, and from there it will move to 1, and 1 after that we will move to 3. Yeah, you guess, you like saw, without like using stack, we are able to trace back our nodes to the root, like to the parent node only. Yeah, so that's how like this Morris traversal, like this Morris traversal is working. So like it's very like it's go like it's a, like like optimized version of this recursive in algorithm. If we consider the time complexity for this algorithm, it's going to be O of n, because like we are what we are simply doing is we are visiting each node twice. You have like already observed this thing. First we are like traversing the node once to get the rightmost node, rightmost last node, then we are like traversing up to the parent. So what we are doing, we are traversing this thing twice. So the complexity will be like O of n, like we are traversing, sorry, twice. So like it's gonna be O of 2n, but like we ignore the constant factor, so it's simply reduced to O of n. So we don't take this complexity, we ignore all the constant factor in like that has been added or subtracted to the complexity. So if the complexity is coming like your complexity is coming something like this, let me, yeah, then this like overall we can say it is over. So this is like an important statement. If big of n is like a times n plus minus b, we can say that it's complexity of O of n. So you can observe that recursive was also solving this problem in O of n time complexity. So what's difference between this recursive between Morris traversal and the recursive problem? The difference come in like especially in the space complexity. The space complexity for this Morris traversal is O of 1. Why? Because we're just maintaining two variables, the root variable, and we need one variable to maintain the leftmost, sorry, it's last rightmost node. So like only we are using two variables, that's why the time complexity of this problem like traversal is O of 1, which is much better than O of n that is in the recursive problem. So that's why like it's very like impressive if you tell the solution in the interview, because you're like first you need to tell the recursive solution in the interviews, then you need to tell this Morris traversal as a like optimization. So this will create a very positive impact on your interviewer, like if you're telling the solution. So you can look at the solution. I've tried my best to explain to you, and if you like find any difficulty understanding it, you can refer to the it is mentioned in the LeetCode official solution for this problem. You can check that there also. I will show you the solution now. So this is like the Morris traversal for this problem, like Morris traversal for this, not this problem. This is the like Morris traversal. So as I already told you, like we are going to maintain like two variables. Let's quickly discuss this solution. Like, so like this is the answer vector we need to return. The same thing we are doing in the recursive solution. So it's same. Then we are maintaining two variable, current and the last. So current is for the root and the last is for the rightmost node. So these are the two variable. That's why the space complexity was coming often. We are like then we are doing we are checking until the current pointer is not null, like this while loop will run. So let's talk about this case like a little bit later. First we need to move to this case. So what I told you, first traverse to the left part of the subtree. So like if this is the tree, our tree. Okay, 6 first if okay, let's consider this case also, like else you will be confused. If the current yeah, this the current node will be here now. If the current of left is null, then we have to just print that node. So this answer dot puts back, I already told you, is like printing the node. But LeetCode like want to want us to give a vector output so that it will handle the printing part. So here it is, we are printing the current node, then we are moving to the right part. So our like current dot left is not null. So what we are doing, we are just making the current dot left as the last node. So in this case, our like current dot left is not null. We are moving to the else block. We will set a last pointer as current dot left, and this while loop, what it will do, it will move to the rightmost last node. So in our case, the rightmost last node is 2. So it will not it will not go further. So from here we will set the rightmost last node as 2, and if the rightmost last node of like the last in like after this loop while loop, we in the last pointer we get the rightmost last node. So we check a solution, like if this rightmost last node is visited once, or like we are revisiting it. So if it is visited once, then the last dot right will be null, because we already discussed about like creating links. So if this link is not created, we are visiting this last pointer once. So this basically this if condition will check that. And if we are visiting the last pointer once, what will we do? We will print the current pointer. So we will print one again, but not again, like for the first time only. Then we will point this current variable, like the last right variable to current. So it will like tell us that we have visited this last node, and we don't need to visit it once more. Then we will move the current pointer to the left. Okay, so current pointer will shift to the 2. And if we have visited the last node, like we are visiting the last node for the second time, so it's this thing, last dot right will not be null. So it will have some value. We will unset that value, and we will move to current dot right. Okay, and after that we will return the answer. So this was like the Morris traversal for this problem. What I have tried my best to like explain this thing. Like if anything is unclear to you, you can just ask me in the comment section. I will try to answer that thing. Like I will also like attach the solution of this both solution in my description. You can check that out. And like having any doubt, you can just make a comment, and I will try to answer it. Okay, yeah, that's all from my side. Okay, bye.